Welcome back to Basic Electronics. In the last lecture, we have introduced phasors and seen how to interpret them in the sinusoidal steady state. In this lecture, we want to apply phasors to RLC circuits to figure out the steady state currents and voltages. In addition, we will look at the maximum power transfer theorem for RLC circuits in the sinusoidal steady state. So let us start. Let us now look at how we can use phasors in circuit analysis. The time domain KCL and KVL equations, sigma ik equal to 0 and sigma vk equal to 0, can be written as phasor equations. Sigma ik equal to 0, where ik are current phasors now, and sigma vk equal to 0, where vk are voltage phasors in the frequency domain. Resistors, capacitors and inductors can be described by V equal to Z times I in the frequency domain, which is similar to V equal to Ri in DC conditions. The only difference is that we are now dealing with complex numbers when we talk about this equation. An independent sinusoidal source in the frequency domain behaves like a DC source. For example, for a voltage source, a sinusoidal voltage source, we can say that the phasor Vs is a constant, which is a complex number. For dependent sources, a time domain relationship such as I of t equal to beta times Ic of t translates to the phasor relationship phasor I equal to beta times phasor Ic in the frequency domain. So the equation looks very similar, except we have complex numbers here. So from all of these remarks, we conclude that circuit analysis in the sinusoidal steady state using phasors is very similar to DC circuits with independent and dependent sources and resistors. And therefore, all the results that we derived for DC circuits are valid also for sinusoidal steady state analysis. Therefore, series parallel formulas for resistors, nodal analysis, mesh analysis, Thevenin's and Norton's theorems can be directly applied to circuits in the sinusoidal steady state. The only difference, of course, is we are now dealing with complex numbers. Let us now consider an RL circuit in the sinusoidal steady state. We have R and L in series. The impedance of the resistor is R, as we have seen before, and the impedance of the inductor is j omega L. This is our sinusoidal source voltage, Vm angle 0, that is Vm cos omega t in the time domain. And we are interested in this current. When we use phasors, this becomes an extremely simple calculation, as we will see. Let us imagine that we have a DC circuit with a DC source here, Vs, a resistor R1 here and a resistor R2 here. What would the current be in that case? The DC current? It would be simply Vs divided by R1 plus R2. So we can use exactly the same equation, except instead of Vs we have a phasor source now, that is Vm angle 0, and instead of R1 and R2 we have R and j omega L, the impedances of the resistor and the inductor. Alright, so then we can write I as Vm angle 0, this source, divided by R plus j omega L, as simple as that. We can write this phasor current as Im angle minus theta, where Im is the magnitude of this expression, and that is simply Vm divided by the magnitude of the denominator, which is square root R squared plus omega squared L squared. The angle of the denominator is tan inverse of omega L by R, and the angle of the numerator is 0. So the net angle of I is 0 minus tan inverse of omega L by R. That is how we get this minus sign over here. So theta here is tan inverse of omega L by R. In the time domain, we have I of t equal to Im cos omega t minus theta. Im is given by this expression and theta is this one. Alright, now let us take some component values, say R equal to 1 ohm L equal to 1.6 millihenry and F equal to 50 Hertz, then theta turns out to be 26.6 degrees. And here are the plots for the source voltage and the current. This is our source voltage. Vm is 1, so it is 1 times cos omega t. And this is our current, the dark one. And let us now try to understand this current plot in terms of this equation. Our Im value turns out to be about 0.9 ampere, and therefore we see that the current goes from minus 0.9 amperes to plus 0.9 amperes. Alright, and as we have said earlier, theta is 26.6 degrees. Now how do we relate this value to this plot? This is an angle and this is time over here. So what we can do is to convert this angle to time. We know that 360 degrees corresponds to one period, and that in this case is 20 milliseconds, because 1 over f is 20 milliseconds, and therefore we can use that fact to find the time that corresponds to this angle. That turns out to be 1.48 milliseconds. Okay, now let's get back to this equation, I of t equal to Im cos omega t minus theta, and ask the question, when does this I of t go through its peak? That is, when is omega t minus theta equal to 0? And the answer is, that happens when t is equal to theta divided by omega, and that turns out to be exactly 1.48 milliseconds. Alright, so what it means is that the current does not go through the peak here when the voltage goes through its peak, but a little later, that is at 1.48 or nearly 1.5 milliseconds, and that is why we say that it lags the source voltage. Notice how easy this entire calculation was. We did not write down any differential equation. We simply used this expression, which is like two resistors in series, and then we managed to get all the information that we required. So that is how phasors really help in analyzing circuits in the sinusoidal steady state. Alright, so here is the circuit file. You can simulate the circuit and maybe change some component values and look at the results. Let us now represent the KVL equation, that is Vs equal to Vr plus Vl, in a graphical form in the complex plane using a phasor diagram. And to do that, we require Vs, which is Vm angle 0, and Vr, Vl. Let us look at Vr first. What is Vr? Vr is I times the impedance of the resistor, which is R. So that is R times Im angle minus theta, because our I is Im angle minus theta. What about VL? VL is I times the impedance of the inductor, which is j omega L. Now this j is nothing but angle pi by 2, and I is Im angle minus theta. So therefore this quantity is omega Im times L angle minus theta plus pi by 2. So this is our phasor diagram. This vector is Vs, and Vs has angle 0, therefore it is along the x-axis, that is the real part of V. Alright, this is our Vr, and Vr has angle minus theta, that means theta in the clockwise direction, and this is our VL. What is the angle of VL? It is minus theta plus pi by 2, that means we go clockwise by theta and then we go anti-clockwise by pi by 2. That brings us to this angle. Alright, and now this equation Vs equal to Vr plus Vl is essentially a vector equation. If we add Vl and Vr, then we get Vs. Next, let us take an RC circuit, a series RC circuit, and this can be analyzed in exactly the same manner as the RL circuit which we just saw. What do we do in this case? We replace the resistor with its impedance, which is R, the capacitor with its impedance, which is 1 over j omega c, and then we can obtain this current as Vm angle 0 divided by R plus 1 over j omega c. That we write as Im angle theta, where Im is given by this quantity. You should really verify this, and theta is pi by 2 minus tan inverse omega Rc. Now this tan inverse omega Rc can vary from 0 to pi by 2, and therefore this angle is basically a positive angle. In the time domain, we write the current as Im cos omega t plus theta, and now let us calculate theta for some component values. Say R equal to 1 ohm, C equal to 5.3 millifarad, and F equal to 50 Hertz. For this combination, theta turns out to be 31 degrees, and that corresponds to a time of 1.72 milliseconds. Alright, now let us ask this question: when does I of t go through its peak? And that happens when omega t plus theta becomes equal to 0. That means t is equal to minus theta divided by omega, and that time is exactly 1.72 milliseconds. Okay, let us look at the plots now. This light curve is the source voltage, 1 angle 0, and it goes through its peak at t equal to 0 because that's the cos function. This dark curve is the current, and that goes through its peak when t is equal to minus 1.72 milliseconds, as we just discussed. In other words, the current goes through its peak before the source voltage goes through its peak, and that is why we say that the current leads the source voltage, since the peak of I of t occurs theta by omega seconds before that of the source voltage. Let us draw a phasor diagram to represent the KVL equation in this case, that is Vs equal to Vr plus Vc. What is Vr? I times R, where I is Im angle theta. So therefore Vr is R times Im angle theta. What about Vc? Vc is I times the impedance of the capacitor, which is 1 over j omega c. Now 1 over j is the same as minus j, that is an angle of minus pi by 2, and therefore we get Vc equal to Im by omega c, that is the magnitude, and for the angle we get theta, which comes from I, and then we have this minus pi by 2 coming from this 1 over j. And as we mentioned earlier, our theta is a positive angle between 0 and pi by 2. Alright, with that information we can now draw the phasor diagram. This is our Vs, and that is along the x-axis because it has an angle of 0. What about Vr? Vr has got an angle theta, which is positive and between 0 and pi by 2. So that is what Vr looks like. What about Vc? Vc has an angle of theta minus pi by 2. So we go anti-clockwise by theta and then we come clockwise by pi by 2. That brings us to this angle. So that is our Vc, and now we can see that the vector equation Vs equal to Vr plus Vc is satisfied. This is our Vs, so Vr plus Vc brings us to Vs. So this is the phasor diagram corresponding to this KVL equation in this case. Let us consider a little more complex circuit now, the one shown here. So we have a sinusoidal voltage source 10 angle 0, frequency 50 Hertz, and we want to find these currents Is, Ic and Il. Step number 1, we convert all the components to their impedances. So this 2 ohms of course remains 2 ohms, 10 ohms remains 10 ohms, 2 millifarads becomes Z3, where Z3 is 1 over j omega c. That turns out to be minus j 1.6 ohms. 15 millihenry becomes Z4, where Z4 is J omega L. Omega is 2 pi times 50, that is L. So that turns out to be J 4.7 ohms. And now next step is we can calculate the equivalent impedance of this combination, and this is exactly like series parallel resistor combination. We have Z2 and Z4 in series, that combination in parallel with Z3, and the whole thing in series with Z1. So that is what Z equivalent is: Z1 plus Z3 parallel Z2 plus Z4. You are definitely encouraged to go through all of these steps and arrive at this final result for Z equivalent. But also look up your calculator, and it is possible that you will be able to do this calculation in a smaller number of steps depending on what your calculator allows. Alright, now let us go ahead. So we have come up to this step. We have found Z equivalent. We already have Vs. So now we can calculate Is. So Is is Vs divided by Z equivalent. Vs is 10 angle 0, and Z equivalent from the last slide is this number here. So that turns out to be 3.58 angle 36.8 degrees ampere. Once we get Is, we can now get Ic by using the current division formula. That is Ic equal to Z2 plus Z4 divided by Z2 plus Z4 plus Z3 times Is, like that, and that turns out to be this number. What about IL? We can get IL in two ways. One, Is minus Ic gives us IL by KCL, or we can use the current division formula. IL is equal to Z3 by Z3 plus Z2 plus Z4 times Is. Either way, you should get this number for IL. And now let us draw the phasor diagram which describes the KCL equation at this node. Here is the phasor diagram, and notice that we have used the same scale for the x and y axis. That is, this distance, which represents 1 unit on the x axis, also represents 1 unit on the y axis. And we do that so as to represent angles correctly. That means a 45-degree angle would indeed look like a 45-degree angle if we follow this practice. Alright, let us now verify whether the KCL equation at this node is satisfied. What is the equation? We have Is equal to Ic plus IL. Our Is is 3.58 angle 36.8 degrees. That is this vector. Its magnitude is 3.58, and this angle is 36.8 degrees. Ic has a magnitude of 3.79, so a little bit larger than Is, and an angle of 44.6 degrees. That is Ic. This angle is 44.6 degrees. IL is much smaller in magnitude, 0.546, and it has a negative angle, minus 70.6 degrees. So that is our IL. And now we see that Ic plus IL is indeed equal to Is. So that means KCL is verified. We have looked at the maximum power transfer theorem for linear DC circuits. Now let us look at maximum power transfer in the sinusoidal steady state. So let us consider a circuit whose Thevenin equivalent is given by this circuit here, namely a voltage source VTH in series with an impedance ZTH. Both of these of course are complex numbers. Now we connect a load impedance to this circuit, and as a result a current is going to flow, and that current is denoted by this phasor I. We want to find the condition for which the power transferred from this circuit to ZL is maximum. Alright, let us begin with ZL equal to RL plus JXL, where this is the real part of ZL and that is the imaginary part of ZL. And similarly, let ZTH be RTH plus jxth. Let I be Im angle phi. Im is the magnitude of this phasor I here, and phi is its angle. Now the power absorbed by ZL is given by P equal to half Im squared RL, where Im is the magnitude of this phasor I and RL is the real part of ZL. What is Im? It is the magnitude of I, and what is I? It's simply VTH divided by ZTH plus ZL. So we get P equal to this expression over here. Let us rewrite this expression as half mod VTH squared divided by RTH plus RL squared plus XTH plus XL squared, and that multiplied by RL. Now this VTH squared is independent of ZL, and as far as we are concerned, that is just a constant. So what we need to do now is to find conditions on ZL for which this whole expression is maximum. Now for P to be maximum, clearly this denominator must be minimum, and that will happen if XTH plus XL squared is 0. Because there is a square here, the smallest value that this term can take is 0, and therefore that gives us XL equal to minus XTH. And with XL equal to minus XTH, this second term disappears and we get P equal to half mod VTH squared divided by RTH plus RL squared times RL. So for maximum power transfer, we need to maximize this expression now. How do we do it? We differentiate P with respect to RL and we equate dP dRL to 0, and then find that P is going to be maximum when RL is equal to RTH. So we have two conditions. One, the imaginary part of ZL, that is XL, must be equal to negative of the imaginary part of ZTH, that is XTH, and the real part of ZL must be equal to the real part of ZTH. To summarize, for maximum power transfer to the load ZL, we need RL equal to RTH and XL equal to minus XTH. That means our load impedance must be the complex conjugate of the Thevenin equivalent impedance, that is ZTH. So ZL must be equal to ZTH star. Let us now look at an application of the maximum power transfer theorem for sinusoidal steady state. Here is an audio amplifier driven by an audio input signal. So the frequencies here would be in the range 20 Hz to say 16 kHz or so. This audio amplifier is followed by a transformer, and we will soon comment on why this transformer is required. And then finally we have this speaker. This speaker has a complex impedance which varies with frequency, but in the audio range its resistance is more or less constant, typically 8 ohms, and its imaginary part can be ignored. So the equivalent circuit representing this entire situation is given by this circuit here. This source here represents the input signal amplified by the gain of the audio amplifier, and then this 1K resistance here is the output resistance of the audio amplifier, and then we have the transformer with a turns ratio N1 to N2, and finally the speaker, which is represented by this 8 ohms resistance here. Our objective, of course, is to maximize the power transfer from this circuit to the speaker. That is how we will hear the loudest sound that is possible with the given input signal. Alright, so let us simplify this circuit. We can transfer this resistance to the other side of the transformer, and then it becomes N1 by N2 squared times 8 ohms. Here is our actual problem statement. We look at this circuit and calculate the turns ratio to provide maximum power transfer of the audio signal. What is the maximum power transfer theorem? It says that ZL must be equal to ZTH star, And in this case, since the imaginary parts of ZTH and ZL are 0, all it means is that the real parts must be equal. That means we must have n1 by n2 squared times 8 ohms equal to 1k, like that. And we can now solve this equation for n1 by n2, and that gives us n1 by n2 of about 11. So if we pick a transformer with this turns ratio, then it is guaranteed that the audio signal will deliver maximum power to the speaker, and we will hear the loudest possible sound that is possible with this input signal. In conclusion, we have seen how to use phasors to analyze RLC circuits in the sinusoidal steady state. This background is going to be very useful when we look at filter circuits a little later. We also looked at the maximum power transfer theorem for RLC circuits in the sinusoidal steady state. We considered an example which is very important in practice, namely how to obtain maximum audio power from a speaker. That is all for now. See you next time.